I'm happy to see you. I'm honored to give the first deep talk of 2023. And the deep talk will be about key point detection and description. I'll tell you about why I believe that's interesting and why that's important. And we had a similar deep talk some time ago. That it sounds like it's similar about landmark detection, but it's not the same thing. So stay tuned, please. Okay. So I'll start with the very basic concepts of what the key point or a descriptor is. We'll be describing descriptors. I'll talk what can we use it for, and I'll go through a couple of algorithms for finding and describing the key points using handcrafted descriptors, using machine learning methods, and using deep learning methods. And I'm aware that I haven't said who I am. So my name is Patryk Kowalski, and I'm a data scientist in DeepSense. Okay, so a key point on an image, also known as an interest point or a salient point, is a two-dimensional location in an image which is stable and repeatable from different lighting conditions and viewpoints. What this means is we have a couple of images of the same scene. In this case, we can see a mountain range, and two images with similar weather conditions and similar illuminations, but a bit different viewpoint, different scale maybe, and different angle. And we'd like our algorithm to be able to find the same key points in both of the images. Of course, there are more common points than just these 8 that's been found, but for some reasons, known only to the algorithm, those 8 are the most distinct and the easiest to match between images. And it's not enough just to find those points. We also need to describe them to be able to match the key points between different images. So we need a descriptor for that, and we can think of a descriptor as a vector embedding for a key point. So let's say we found them. What do we need them for? I'd say there are like the basic low-level applications, and I'd like to tell you about 2 of them. Like the first one is matching scenes, where let's say you have a scene, you have an image, and you have a whole data set of images containing different scenes. And you'd like to filter out from this data set only the image of your location that you're interested in. Like you have images of different shops, for example, or of different things whatsoever. So by matching your query image to all the other images, you can see how many points are common between those 2 images. You can try to match the points, and the pairs of images with the most key points common are probably showing the same scene. So that's not like object detection, because you do not need to have predefined objects. You're just looking for similarities between 2 images. And you can do a homography transformation, a perspective transformation. I actually have prepared an example of that. So I have my deepsense.ai bug, and I have a piece of paper that there is something written on the piece of paper, and I have taken a photo of this. But the photo isn't too good. The angle is messed up, it's too close to the floor, and I'm not able to read what is written on this piece of paper, and I'd like to know. So I go back to this bug, and I take a photo from the top. So now I would know what is written on the piece of paper, but the piece of paper is not there anymore. It got lost in the meantime. So does it mean I will never know what was written on the piece of paper? It doesn't, because I can perform a perspective transformation and transform the image on the left to the photo on the right perspective and see how the photo from the left would look like from the top. And now it's easy to read that the piece of paper actually says deepsense.ai. That's a silly example. It's not used this way in like real case business scenarios, but it can show you that it has potential for pre-processing images, for example, for like more serious approaches. And yeah, zoom and enhance would work as well in this case. I just wanted to show you an example of a perspective transformation. And in order to do that, I had to find the key points between 2 images, and those are the pairs that were selected by the algorithm, pairs of key points. All right, and to perform this kind of perspective transformation, we need a homography matrix. That's a 3x3 matrix that actually only has 8 degrees of freedom because it's derived from pinhole camera model. That's like an easy special case. And if we have a point and a homography matrix, we can perform multiplication and get projection of this point. in the new scenery. And we need at least 4 pairs of corresponding points to solve this equation and actually get the homography matrix. Although having more points is always better, because we can always pick the best 4 pairs from any number of points using, for example, ransack algorithm. And more serious applications than the 2 low level I was mentioning before. Most well known is probably the panorama stitching. That's old. And that's where you have a series of images and you'd like to turn them into one panoramic image, like here, to get like the wider mountain range. There is 3D reconstruction, where you have a series of images from different angles of an object, and you can turn it into a 3D model representation of the object. There is visual localization, where you have an image of an object and you already have a 3D model of the object, but you'd like to know where exactly is the object from your image in your model. So you want to localize it, or you can just have a discrete database of images and you'd like to localize your query image in that database. So that would work too. And there is SLAM, simultaneous localization and mapping, used in robotics, where a robot simultaneously localizes itself and constructs a map of the unknown environment. In the image here, you can see examples of trajectories estimated by robots, like video recording of what a robot can see using different algorithms. Okay, so we know what it is, we know what it can be used for, but how to do it. So the most well-known algorithm for that is SIFT, that was described in a paper in 2004, even though that was first used in like 1999 by its author, and it's not machine learning related at all. To perform SIFT, you need to find key points. The key points have x and y coordinates in an image, and they do have a scale. We use difference of Gaussians for blob detection, which means that we blur the image with different sigmas. So we create like a ladder of images blurred on different stages of being blurred, right? And we look for local extrema over scale and space. Over space, that means we just look side to side for neighbors where there are big differences. And over scale, we look in the image that is one stage more blurred and one stage less blurred to find in which scale the key point is the most distinctive. There is like the biggest extrema. So at this point, we do actually have our key points. We now need to describe them. To describe them, to assign a descriptor, we assign orientation as the most common orientation in the key point neighborhood. Orientation is calculated as a gradient. And we don't just need this orientation, we actually need this orientation referred to the key point's neighborhood. This way, the key point is rotation invariant, because you're not just looking at its orientation, you're looking at its orientation relative to things that would rotate alongside with it if you were to rotate the picture. And we generate a descriptor using illumination and orientation histograms of key point neighborhood relative to the key point. So we check lots of orientations around the key point. If the key point has a big scale, then we look at a big neighborhood. If the key point has a smaller scale, we look at a smaller neighborhood. And we use histogram of the orientations to create a distinctive descriptor. Some of you might have already heard of SIFT because that's very, very well known in computer vision, but maybe haven't used it because it used to be patented and not free for commercial use. So that's not the case anymore since, I guess, March 2020. So you're free to use it if you want to. And one of the first machine learning approaches, not deep learning, but machine learning, was called TILD, a temporally invariant learned detector. TILD is trained using AMOS dataset, where AMOS stands for Archive of Many Outdoor Scenes. That contains webcam records. It's good that those are webcam records because that means that for any location you have on the video, you know how this location looks like in different weather conditions, in different illumination, at different time. And this way we can make the detector better than SIFT because, for example, SIFT only can find key points in this location when it's light, when it's bright outside. And when it's darker, it doesn't find them. So in this case, we can compare all of the snapshots, all of the frames we have for this location, and we can superset. We can estimate where the key points are, even though SIFT doesn't recognize them, because we know they were there when it was brighter. So they have those images, and they split it into a grid, into multiple patches. And they actually use SIFT to estimate which locations contain useful features. But the positive examples are not only the images where SIFT found key points, but also the locations where we know SIFT finds key points in many cases, but not always, right? So we look for the most repeatable key points, and the locations that key points weren't found there, but we know they could be there, are actually the ones where we can enhance our algorithm, where tilde will be better than SIFT. The features for the function, those are components of the color space, image gradients, gradient magnitudes, and they fit a piecewise linear function to it. It's a regression, so the idea is to have a big value of this function if the patch contains a key point in the center of it. If the patch contains a key point but not in the center of it, then the value should be smaller. And if the patch doesn't contain a key point at all, then the value should be very small. So this way we get like this map of probability of key points in every patch, in center of every patch. And the loss function is, well, for one thing, it's based on the distance from the key point, because, yeah, as I said, if the key point's in the center, then it's good. But also the location score repeatability. So if we know the key point should be there, then we like the model to always find the key point there. Doesn't matter what the illumination is. So yeah, that was one way to make the SIFT a bit better. And the tilde detector was used in 2021 in a more complex architecture of like 4-branch Siamese network. One piece of this network is the detector, the first one. So this detector is actually the tilde detector. And if you remember that SIFT is used in tilde detector and tilde is used in this newer detector, then we can see that the ideas here, like we get a nice build-up of ideas. And even in the most recent architectures, all the ideas are still being used. Okay, so we are at deep learned descriptors, the dense deep learned descriptors. Those are neat because dense pixelized features naturally emerge from CNNs. Like we understand the convolution layers. We understand that convolution layer can serve as a descriptor of the image. So that's the basic idea. We start with the most abstract convolution layer, the fifth one in this image, and we look for the closest descriptors between two images in this layer. Once we find a good potential match, we can go in a coarse-to-fine approach to the previous layer and the previous layer to increase the spatial accuracy and the resolution. So this idea was used in Structure from Motion paper from 2018. But that is a dense representation, and we also have, and we actually prefer, a sparse representation. So there is a SuperPoint network. That's from their website, and here they showcase on a video that they are able to find stable key points and track them throughout the movement. And SuperPoint is a pretty important paper. It introduced two novel ideas. The first one is, well, actually, it's about the base of this whole key point idea, because key point is semantically ill-defined. It's not like the face landmark where we do have a nose, where we do have ears, and we can get a human annotator to mark them on an image. In this case, we don't know what a good key point is, because it is good if it's good for matching, but we don't know what that means as humans. So it's hard to create a good data set for supervised learning, right? And SuperPoint authors figured out that they can have a dataset for supervised learning if they create the dataset themselves and if the images are simple enough to have no ambiguity regarding interest points. So they created a dataset they called synthetic shapes that contains many simple synthetic shapes where key points are the corners, like the most interesting parts of the figures. And they trained a Bayes detector on those points. Is this Bayes detector, will it generalize well to actual world images? Well, it won't at first, but it will find some key points in real-world images. So they found out that if they perform a homography on an image, they perform 100 of homographies. They call it homographic adaptation. And they apply the base detector to every version of the image, every slight perspective warped image. Then the base detector detects a bit different key points every time. And they can superset all of those key points to the original image. And then we have a pretty thorough representation of every key point we can find in this image. I'll take a short break here to answer the question I see appeared. Conrad, are deep learning based descriptors really beating classical ones at the moment? I was doing some research about this few years ago, and back then classical ones were doing slightly better. Deep learning ones were winning on some datasets, but were not really generic enough. So it really depends on an application and what kind of images you have, because sometimes like you have indoor data sets that have some, I don't know, maybe small variance between illumination, and then it's possible that your classical algorithm will perform as well as the new deep ones and will be less computationally expensive. But in most cases right now, I think the newer architectures win, and that's also the case with the example I've been showing you with the deepsense bug transformation, because I tried to use SIFT, I tried to use even this SuperPoint I'm talking about right now, and I wasn't able to get good results until I reached for even newer architectures. So to summarize, depends on your application. I'd say you always have to check a couple of algorithms to see what works best for your particular case. But in general, I think deep learning based descriptors are beating classical ones at the moment. And there are always hybrid ones, like you have the Kinet deep detector that actually, or maybe descriptor, no, detector, that actually uses handcrafted and learned filters to find the key points. So the hybrid approaches are even better. Okay. So now we have a detector that is made better by training on real-world images, and we can actually retrain the base detector on the pseudo-grand truth set that we've achieved by finding the key points on the real-world images. We can iterate this process. We can do this a couple of times to get an even better detector. That's the architecture of the detector they used. There's a backbone encoder, VGG style encoder, and there is interest point decoder. They don't use learned upscaling, they use just normal pixel reshuffle upscaling. So after an image goes through an encoder, its dimensions width and height are smaller 8 times, but the depth has 65 channels. 64 of these channels are just for upscaling, so you can reshape it into 8 by 8 pixel, and that's how you get into the original image shape. And the 65th dimension is a garbage bin. So if there is a key point in this cell, then it should be assigned to one of those channels. And if there isn't a key point, it should be assigned to this garbage bin channel. So the output here corresponds to probability of for every pixel of being a key point. And there is a descriptor, very similar. It shares the backbone. But to train the descriptor, we need a joint training, where we get a pair of images. We warp one of the images a little bit, again, using homography. And we know where the key points go, because we had the key points first, and then we perform the homography, right? So we know where they are in both images, the exact same key points. And we teach the network to minimize the distance between descriptors for the same key points, but on slightly different images. Yeah, so that's how it works. There is also an upgraded approach from 2020, totally different. It's end-to-end, where it doesn't return you key points and descriptors, but it performs matching between images. And it's a complex architecture with graph neural networks, with self and cross attention, and we won't be going into details here, but it's a good read if you'd like to look into that. Okay, so we're nearing the end. I'll just tell you how I made the example, and we'll be done. As I said, answering to the question, I tried SIFT first, and I tried superglue first, and the results looked something like this. So I couldn't really use perspective straight from the top because it was too far away. I had to like compromise and get a smaller angle, and still the result didn't look very well. But for some simpler applications, OpenCV is enough. So if you want to try, then OpenCV has some easy tutorials, and you can use SIFT to perform this transformation. In some cases, that will be enough. What I ended up using was a Cornea library that has some ultra high-level functions for performing this stuff. So this code stub that I pasted here is actually enough to recreate the example that I did. And it's in their example. So if you'd like to look into that, then there is a link at the bottom. And I tried to look a bit into what actually is behind this keynet, offnet, hardnet method. And they use two detectors for that. There is this keynet that I mentioned as a hybrid approach that uses both handcrafted descriptors and learned descriptors. There is an offnet detector that is interesting because it works a bit differently. It uses affine transformation of local features to find an affine invariant shape. So it tries to find like a small transformation matrix for small key points to find the shape that is invariant to transformations. There is a hardnet descriptor that is actually a CNN, but they use some fancy distance, fancy loss function where they calculate a distance matrix between many different patches, and they find the most useful trio to calculate the triplet loss. And there is a fancy outlier detection algorithm to figure out which matches should be dropped, and that's called Adalam. And that uses some local consistency constraints to make sure that the matches make sense and that resulting perspective transformation would also make sense. And that's about it. Thank you for your attention and for listening. And I think we're done for today.